So this video is going to be covering Chapter 18, Section 4, which deals with solubility equilibrium. And what you have to realize is that in some sort of solution where you have a ionic compound made of, a cation and an anion breaking up into their constituent aqueous parts, that this is actually a reversible reaction. In other words, you have the compound breaking up into its ions, yes, but these ions also recombine to form the compound. And this reaction reaches an equilibrium just as all reversible reactions do. And so what you have to realize is that these ion concentrations, much like the concentrations of products and reactants previously, can be used to find an equilibrium constant, just as we did with standard chemical reactions. Constant. And this constant can be used to predict whether or not something will precipitate out of the solution. So moving on now, we're going to be discussing the concept of solubility product. And before we do that, we have to say that we're going to be looking at mostly saturated solutions. Now, a saturated solution has the maximum amount of solute for a certain amount of solvent. Now, it's important to note that saturated does not mean the same as a concentrated solution. For example, something could be only slightly soluble, or insoluble rather, if it only dissolves 0.1 grams of solute for every 100 grams of solvent. So that would be what we would call insoluble. Likewise, you could have something that dissolves 1 gram for every 100 grams of solvent, and we would call that soluble. And you could dissolve in this 1 gram, and there could still be room to add more if it were a super soluble solvent. If it's somewhere out in between these two, it's what we call slightly soluble. And for the most part, we're going to be looking at slightly soluble and insoluble solutes for the purposes of this video. As an example, if you were to take silver chloride as a solid powder or whatnot and dissolve it into water, you'd end up with positive silver cations and negative chlorine anions rather. However, silver chloride is only slightly soluble. So as a consequence, you'll very quickly reach this equilibrium, and you'll all the excess you add after that equilibrium, which will be most of the silver chloride, considering it's a very tiny amount that actually dissolves, will precipitate out. And that is, it will form a solid that will just float to the bottom. So just as we've done previously with full-on chemical reactions, despite the fact that you aren't really changing much in this, you're just adding a compound to a solution, we can write an equilibrium equation, because this is, after all, a reversible reaction of sorts. And the equilibrium equation uses the variable Ksp, which basically means the solubility product constant. And we follow the same rules as we did for chemical reactions. In other words, we don't include pure solids or pure liquids. So in this case, the solubility product constant for this dissolution of silver chloride would be the concentration of Ag plus times the concentration of negative chlorine. And you would, if there were, if this were some sort of compound that had 2 chlorines, and then you would have 2 over here, you'd raise it to that power. You do the coefficient as an exponent once again. Now the other thing is that the solubility product constant has to be determined experimentally. In other words, it's hard to predict what exactly the Ksp will be for a certain dissolution. So, if from experimentation we determined that the maximum amount of silver chloride soluble in 100 grams of water was 1.9 times 10 to the negative 4th grams, we could determine exactly the molarity of that solution for the silver chloride through this process. Basically what you do is you take your 1.9 times 10 to the negative fourth grams of silver chloride for every 100 grams of water, and then you just solve for the molarity. So you get the volume of water through these steps here, and then you get the moles, basically using the molar mass of silver chloride, and cancel out the masses of the silver chloride to get 1.9 times 10 to the negative fourth times 1,000 moles for every 100 times 143.32 liters of water. And what you end up with is a 1.3 times 10 to the negative fifth molar solution. Now from there you can determine the Ksp value. Now because silver chloride breaks up into equal parts silver and chlorine, that is, there's only one ion of silver and one ion of chlorine in each, we therefore know the concentration. We don't have to use any exponents or anything, any hard math. So this basically comes out to be 1.3 times 10 to the negative fifth, and then because chlorine is also 1.3 times 10 to the negative fifth molar, we square the whole thing, and you end up with a Ksp value of 1.7 times 10 to the negative 10. Now that we've seen how to calculate the Ksp value, we can use this Ksp to actually calculate the solubility of something. In other words, how soluble it is in a certain solvent. So, for reference, on page 615, there's a great table of solubility product constants for common compounds. And for this example of calculating solubility, we're going to be using barium carbonate, which has a Ksp value at 25 degrees Celsius, because remember it changes with the temperature, of 5.1 times 10 to the negative 9. Now, if we want to see how much barium chloride is soluble in 1 liter of water, we can use the solubility product constant to do so. First things first, we have to write, our equation for the dissolution of barium carbonate in water. So you have, two barium, or a barium ion and a carbonate ion, both of which have a charge of 2, just opposite signs. Now, from here, we just set up our Ksp equation because we have a known Ksp, and so we use the concentrations of barium and carbonate, and this is what we're going to use to eventually solve for its solubility. Now we know this all equals the Ksp value of 5.1 times 10 to the negative 9. And because these each enter in a 1-to-1 ratio, these both have the same value. So if we let that equal x, then the carbonate concentration, also equals x. In other words, you're going to have the same concentration of barium as carbonate for all intents and purposes. So you can set that product as x squared equal to the Ksp value of 5.9 times 10 to the negative 9th once again. And then solving for x, you get the concentration of barium carbonate is 7.1 times 10 to the negative 5 moles per liter. Moving on now, we're going to be discussing precipitation calculations. And as I mentioned before, the solubility product constant can be used to predict whether precipitation will occur. So basically, if the product of the ions, the product of the concentration of the cation and the anion raised to whatever their coefficients are, is greater than the solubility product constant, then you will get a precipitate. And this can often happen if you mix the solution at a high temperature and then you decrease the temperature. Then the Ksp will usually decrease as well, and this will have to, you'll shift the equilibrium back to the left, and you'll end up with a precipitate of this general compound cation anion. Likewise, if your concentration of cation times anion is less than the solubility product constant at that temperature, then you have an unsaturated solution. In other words, you can add more of the compound to the solution until you reach the solubility product constant, and then you'll reach a certain equilibrium. And it should be noted that the Ksp value is really only a useful tool for slightly soluble and insoluble materials. So when you get to super soluble materials, salt, sugar, whatever, it gets a bit sketchy to use the calculations.